I'm Brianna Clark, senior at Thomas Edison State College, majoring in nuclear energy engineering technology, and a veteran of the United States Navy, where I was trained as a nuclear machinist mate and engineering laboratory technician. In this presentation, I'm going to introduce the liquid fluoride thorium reactor and go over some of its benefits. This is an incredible technology that has the power to solve the current energy crisis facing us, revitalize the nuclear energy industry, and make it much safer and secure the economic and environmental future of this planet. While the liquid fluoride thorium reactor, or LFTR for short, has many different benefits, I'm going to cover three major ones. Its increased safety, its use of the liquid fuel design in reactors, and its decreased waste compared to a normal reactor. Now, safety of a reactor is obviously a very important concern today, especially after disasters such as Fukushima, Chernobyl, and 3 Mile Island. One very important safety characteristic of the LFTR, however, is its negative temperature coefficient. Now, that's a fancy word to say that as temperature goes up, reactor power goes down. This happens because the fluid expands, pulling apart the particles of uranium in the fluid, which means there's less reaction happening. So in case of an accident, such as loss of load, reactor power is going to go back down by itself without operator intervention or safeguards. Another very important safety characteristic is that it operates at atmospheric pressure. The boiling point of the molten salts that are going to be used is greater than 2,700 degrees Fahrenheit. So there's no need for the high pressure, high temperature conditions of a typical pressurized water reactor. Now, because of this, Kirk Sorensen, who's considered an expert in this field and has spent many years researching and promoting this reactor to the public, wrote an article in 2006 that postulated that the LFTR can withstand such critical incidents as loss of containment and breach of reactor vessel. Should the fluid become exposed to the atmosphere, it won't explode, it won't flash to steam. There's no need for the large containment that's used in current pressurized water systems. The only thing that will happen is the fluoride salts will freeze, trapping fission products as stable fluorides. Another concern in that type of emergency is the release of gaseous fission products. Now, because of the unique characteristics of the liquid fuel system, you can continuously remove gaseous fission products. So should there be a containment breach, there just won't be that many to release. Another safety feature that has been built into the liquid fluoride thorium reactor is called a salt plug.
This is a very basic picture of a liquid fluoride thorium reactor from the website thoriumforsingapore.com. The reactor core, heat exchanger, and turbine are all common to both the LFTR and traditional reactors. However, the orange area around the reactor core is a blanket of liquid thorium. The thorium-232 absorbs stray neutrons that escape from the core and then eventually decays to uranium-233. Another structure unique to the LFTR is the freeze plug at the bottom. This is a plug of fluoride salts that are kept frozen by a cooling fan. Should power be lost or the reactor overheat, the plug will melt and the fuel will drain into a subcritical, passively cooled tank equipped to remove decay heat. This helps prevent a reactor meltdown and maintains the removal of decay heat in an emergency.
Now, another concern with nuclear reactors is proliferation. This is when nuclear material is taken illegally from a reactor and used to make nuclear bombs. This is another problem that the liquid fluoride thorium reactor would solve. When thorium-232 is converted to uranium-233, a byproduct of that is uranium-232. Now, uranium-232 is a radioactive isotope which eventually decays into thallium-208. When thallium-208 decays, it emits a 2.6 megaelectron-volt hard gamma ray. Now, this has a very easily detectable signature, and it's very penetrating, harmful to personnel. It's harmful to any electronics, any explosives that might be used in the bomb. It's just not worth it. Furthermore, should any uranium-233 be stolen from a reactor, since there's not a whole lot of excess reactivity, it would be noticed. It would either shut down the reactor or reduce power to an extent that it would be obvious what had happened. Now, I mentioned I had three major benefits that I wanted to cover. The first was safety, which we just talked about. The second was the benefits of using liquid fuel instead of the solid fuel normally used in reactors.
The fertile material used in the thorium blanket is thorium tetrafluoride and a fluoride salt with lithium and beryllium. The fuel used in the reactor core, uranium-233 tetrafluoride and a fluoride salts with lithium and beryllium, is pictured here. It is solid at room temperature.
The use of this liquid fuel is what gives us such a large negative temperature coefficient. Now, some of you may be used to a pressurized water reactor. Well, you still have a negative temperature coefficient. The one in the liquid fluoride thorium reactor, however, is much larger. It's so large that there's no need for absorptive control, such as control rods, burnable poisons. It's very much load following. This, of course, increases the safety and the cost effectiveness of the reactor. Another benefit is that you can continuously remove fission product gases. Like I mentioned before, this is a safety issue. If there's no fission product gases in the solution, there's nothing to release to the atmosphere. However, another large problem in traditional reactors is xenon buildup. Xenon-135 is a byproduct of the uranium-233 decay process. However, it is also a gas. When you can continuously remove it, it will not be absorbing neutrons. Therefore, you'll have no xenon transients, and you don't have to add excess reactivity in order to counteract that.
Another huge benefit to using liquid fuel is that it opens up the possibility of continuous refueling. This is a newspaper clipping showing an engineer pouring liquid uranium fuel into the molten salt reactor at the Oak Ridge National Laboratory, which was the first reactor to ever use liquid fuel.
Being able to continuously refuel the reactor gives us a few benefits. Firstly, there's minimal loading requirements. You don't have to load in a lot of excess reactivity at the beginning of core life. That means the reactor is cheaper to start up and safer to operate. Secondly, there's no need for fuel reshuffling. In a traditional solid fuel reactor, more fuel burnout occurs at the center of the reactor due to the higher neutron flux there. The fuel must be shuffled around to ensure even burnout. Not so with a liquid fuel design. Lastly, there's no downtime for refueling. This is a big cost to most power companies as they have to shut down in order to completely refuel their reactor or shuffle their fuel rods around. With liquid fuel and continuous reloading, there's no need for a downtime. This saves costs, which in turn makes the reactor cheaper to operate. There's also a more thorough burning of fuel with the liquid fuel design. There's a few problems with solid fuel design.
This drawing shows some of the typical problems that solid fuel rods have. There is cracking, uneven expansion and contraction, wide temperature variations. In fact, there's a 1200 degrees Celsius difference between the core and the outside of the fuel cell, and flux variations. Should a fuel cell become damaged, the cladding could crack, resulting in a fuel element failure and fission product release. Liquid fuel faces none of these problems.
The third benefit to the liquid fluoride thorium reactor is decreased waste. Here's a great infographic about uranium versus thorium.
This infographic is from a lecture Kirk Sorensen gave at Google in 2009. To make 1,000 megawatts of electricity in a year using uranium, 250 tons of natural uranium must be mined. This is then enriched, with 35 tons of enriched uranium being used as fuel. 215 tons of depleted uranium is created and must be disposed of. The fuel is burned, and now 35 tons of radioactive waste needs to be stored. Some of this waste will be significantly radioactive for the next 10,000 years. However, to do the same thing with a liquid fluoride thorium reactor requires 1 ton of thorium, no enrichment needed. It is converted into uranium-233 nearly completely and burned. 1 ton of fission products are left, although within 10 years, 83% of them will be stable. Some of these are even valuable elements and can be sold. 17% of the original ton is left, which will be stable in approximately 300 years.
Another area where the thorium reactor generates much less waste than a uranium reactor is in mining. The Thorium for Singapore site estimates that it could be as much as 4,000 times less than mining uranium. Also, since the desired isotope, thorium-232, is the only one naturally occurring, there's no enrichment process. That means no enrichment factories, which cost a lot of money, And there's also no depleted uranium, which can be weaponized. The LFTR can also burn down the waste that we currently have. Since there doesn't need to be a lot of excess reactivity in these reactors, the waste that we have is actually radioactive enough in order to power these. There's also valuable secondary products. This generates a lot of heat. These burn a lot hotter than the typical reactor. This excess heat can be used for economical desalination of water, cracking hydrogen from water and hydrocarbons, and the generation of ammonia for fertilizer and fuel cells. There's also some valuable secondary products that are made from the waste.
There are also some valuable, stable nuclear waste products created. Rhodium and ruthenium, which are rare elements needed for modern electronics, technetium-99, used as a catalyst similar to platinum, iodine-131 and cesium-137 for medical applications, strontium-90 for radioisotope power, and xenon used in commercial products and industrial processes.
So we examined 3 major benefits of thorium: increased safety, use of liquid fuel technology, and decreased waste. And it's true, the liquid fluoride thorium reactor is essentially untested technology. However, so is uranium at one point, and this technology can salvage our future. Thank you.